You hear these terms thrown around all the time, right? AI, machine learning, deep learning. But what do they actually mean? How does a machine really learn anything? Well, today we're going to cut through all the buzzwords and build these ideas up from the ground floor, starting with a problem that's super easy for you and me, but an absolute nightmare for a traditional computer. So let's dive right into that problem. Okay, take a look at this. It's a 6, obviously, but I want you to put on your programmer hat for a second. How would you write a set of instructions, a program, to tell a computer that this is a 6? Where would you even start? You'd probably have to create this just endless list of rules, right? You might code something like, okay, if there's a closed loop at the bottom and a line coming off the top, it's probably a 6. But what if someone writes it and the loop isn't perfectly closed? What if the line is kind of slanted? All of a sudden, your nice, clean rule just breaks. You can see how this approach gets real messy real fast. And now, look at this. Every single one of these is a number we can recognize instantly, no problem. But for a computer that's just trying to follow a strict set of rules, this is absolute chaos. Every single variation would need a new rule, or a tweak to an old one, and you'd literally be writing rules forever. This way of doing things just doesn't work. It hits a wall. We need a better way. And that better way means we have to completely flip our thinking. Instead of giving the computer a giant book of rules to follow, what if we could just teach it to figure out the rules for itself? Now that is the core idea behind machine learning. And here's the big shift. We stop being the programmer who has to think of every single possibility. Instead, we become more like a teacher. We give the machine a flexible framework. We call it a model, and then we just show it tons and tons of examples. We let it figure out the patterns. We let it learn what really makes a 6 a 6. Now, to really get how this works, let's step away from messy handwriting for a minute and use a much simpler problem. Let's say we want to predict whether a student is going to pass or fail an exam based on two things: how many hours they studied and how many hours they slept. So here's our data. Every single point on this chart is a student. Along the bottom, we have hours studied. Up the side, hours slept. The little plus signs are the students who passed. The minus signs, well, they're the ones who failed. You can already see the pattern with your own eyes, can't you? The pass folks are kind of clustered up in one corner, and the fail folks are in the other. Now, for a simple problem like this, our model can be something really, really simple. It can just be a line. That's it. The line's only job is to try and find the best possible way to separate the students who passed from the students who failed. But how does it find that perfect line? Well, any line can be described by a couple of numbers: its angle and where it sits on the graph. We call these parameters. Think of them like little knobs or dials on our line drawing machine. The whole process of machine learning is just the computer automatically tweaking these dials, adjusting the line over and over and over again until it finds the sweet spot that does the best job of separating our data. That tweaking, that's the learning. So we have this idea of a model that draws a line, but what is that model really? Like, what's the actual little engine that's doing all this work? Well, the answer takes its inspiration from the most incredible learning machine we know of, the human brain. Our brains are just packed with billions and billions of these things called neurons. Each one is a tiny little processor. It takes in signals from other neurons, does a super quick calculation, and then decides if it's going to fire off its own signal. It's a really simple process, but when you have billions of them working together, that's where all of our thoughts and learning come from. And this amazing biological design is the direct inspiration for modern AI. And here it is. This is the digital version, a single artificial neuron. It's really just a simple piece of math, but it's designed to act just like its biological cousin. For our exam problem, this is the tiny engine that's drawing that dividing line. And here's how it works. It's pretty simple. First, you feed it the inputs. In our case, hours of sleep and hours of study. Each of those inputs gets multiplied by a weight, which is just the neuron's way of deciding how important each input is. Then, it just adds everything up. And if that total number is above a certain threshold, the neuron fires and says, pass. If it's not, it says, fail. The whole learning part is just the process of finding the absolute perfect weights for those inputs. Okay, so a single neuron is great for drawing a straight line. That's awesome for our simple exam problem. But what happens when we get to more complicated, real-world problems? I mean, what happens when a simple straight line just isn't going to cut it? Look at data like this. You just can't separate the pluses and the minuses with a single straight line. It's impossible. The patterns are curved, they're circular, they're messy. A single neuron would totally fail here. The real world is complicated, and we need our models to be more powerful to handle it. So, what's the solution? Well, it's actually beautiful in its simplicity. If one neuron isn't powerful enough, we don't throw the idea away. We just use more of them. We connect them together in layers. And this is the big jump. On the left, you've got our single little neuron. On the right, you have a whole network. The idea is simple. The outputs from that first layer of neurons become the inputs for the second layer, and the outputs of the second layer become the inputs for the third, and so on. By stacking them, we create depth. And it's this depth that gives the system the power to learn incredibly complex patterns that a single neuron could never dream of. And that, right there, finally brings us to our last big buzzword: deep learning. That's all it is. It's a type of machine learning that uses these deep, multi-layered neural networks. The deep part literally just means that the network has multiple layers, which allows it to learn things at different levels of complexity. So, now we've got all the pieces on the board: artificial intelligence, machine learning, and deep learning. Let's put it all together and see how they fit into the big picture. Here you go. This is how it all relates. Artificial intelligence is the huge, overarching goal, the big dream of building intelligent machines. Machine learning is a specific approach to achieving that goal, where we get systems to learn from data. And deep learning is a very specific and very powerful technique inside of machine learning that uses those deep neural networks we just talked about. So let's just put it simply. AI is the dream. Machine learning is the method we're using to get there, and deep learning is our most powerful tool for that method, using those amazing brain-inspired networks. And it's this powerful structure that brings us full circle. It's what allows a machine to finally learn how to recognize all those messy human-written numbers. But it also allows them to do so much more, from detecting diseases in medical scans, to understanding what we say, and even to driving cars. So, at the end of the day, we figured out how to build systems that don't just follow instructions, but actually learn from experience, a lot like we do. It's a fundamental change in how we think about technology. And it leaves us with one really big and exciting question to think about. Now that we can teach machines to do almost anything, what should we teach them to do next?